Welcome to Geotechnical Engineering Design. This video will be about the resolution of a problem related with the proper wall. So this is after the introduction to the theory of this topic in civil engineering. We're going to do exactly the same exercise we did for improper walls, but this time we're going to consider that the wall is proper. So we're going to have a load Q and favorable variable loads of 10 kilonewton per square meter on top of the ground to the left side of the wall. We're going to have a height of 6 meters for the wall, keeping the ground in this position. The wall is inserted 10 meters in the ground. The dry unit weight of the soil is, which is the sand, is 19 kilonewton per cubic meter, and the angle of internal friction initially is 40 degrees and is a property, the main property for this sand. So in the first place, we're going to review again the Euro codes in terms of advices to increase actions and decrease material properties. As we mentioned in the previous exercise regarding improper walls, the resistances are not affected at all in terms of coefficient, because all the coefficients are equal to 1 for the design approach 1 and combination 2, which is the design approach and combination that the Eurocode 7 advised to use for geotechnical problems. For the case of our load Q, which is an action, is a variable and favorable action. We have in the second column that correspond to the design approach and combination 2, column A2, as you see here, 30% of increment in the value of Q, because it's a variable and favorable action. So we are going to increase this value in order to be safer, in order to be farther from the failure of this wall. So in terms of material properties, we are going to affect in this exercise the tangent of the angle of internal friction with the coefficient 1.25. We're going to see how to apply this coefficient to reduce the angle of internal friction. So this is what I'm going to do now. So as we did before, remember that we apply the coefficient 1.25 dividing the tangent of angle of internal friction, which is 40 initially. After this calculation, we had to apply the inverse of the tangents of this value, 0.671, and we got 34 degrees of the new angle of internal friction, the reduced one. So we're going to change this angle in order to be safer. In terms of the Q, we are going to increase in 30% this Q to got Q prime, which is will be our new unfavorable variable load, and we're going to change to 13 kilonewton per square meters then. And we're going to apply the same good practice we applied before, reducing the distance d equal to 10 meters, the distance that the wall is inserted in the ground, with this coefficient 5/6, and we are going to have then a new distance d prime equal to 8.33 meters. So after the reduction of the distance, the increment of Q, the loads, and the reduction of the angle of internal friction, we're going to calculate with this new angle the coefficient of active pressure and the coefficient of passive pressure using the formulas you have on the screen. After that, we are going to analyze what are the active pressure we have to the left side of the wall. We have the active pressure produced by the increased Q, the unfavorable variable loads. So the base of this rectangle will be Ka, angle coefficient of active pressure multiplied by Q prime. The base of this triangle that represents the active pressure of the ground is coefficient of active pressure times unit weight times the height of the wall, which is d prime times h, and the triangular diagram for the passive pressure is the triangle in red, as you see on the screen. This is the active pressure, the passive pressure to the right, and we can start doing calculations now. So the base of this rectangle will be 0 to 0.28, the coefficient of active pressure multiplied by 13, the new increased load we have on the problem. The base of the triangle that represents the active pressure, because the ground, the self weight of the ground, It's 0.28 times 19, the unit weight, times the height of the wall, the total height, which is 6 plus 8.33, which is 14.33, and this is 76 kilonewton per square meter of pressure. The forces that are the areas of these diagrams are resultant forces of these pressures, so are located in the centroids or barycenter of these triangles and rectangle, as you know. And because this is a propped wall, the mechanism of failure will be a rotation around a point on top of the wall, because we have this P here that is avoiding any displacements in the horizontal direction of this wall because the active pressure. So the only possibility of this wall is to rotate around this point. And this is the reason why we have to take moments around this point to ensure that there is an equilibrium and to work out the value of the passive pressure in equilibrium, basically. So in order to do that, we work out the distances from the points of rotation on top of the wall to every single force of this free body diagram. And basically, we write the equilibrium equation, which is negative moments for the active pressure because they both are producing rotations against the clock, and plus the rotation produced by the passive pressure, which is clockwise, so it's positive then. So forces times distances, all of this equal to 0. We can work out then the passive pressure, and this is the formula, but we need the values of PA1 and PA2, and this is simple to do because we have the formula for and the values for the base of this triangle and this rectangle, so we need to work out the area. You have the formulas in there, or you can do it numerically as well. You have to work out these two values, these areas of these two diagrams, the rectangle and the triangle in blue, and these forces are in kilonewtons. And replacing in the formula for the passive pressure, we got that the passive pressure in equilibrium is 481 kilonewton. This is what we need as a minimum to keep this wall in equilibrium with P and the active pressure to the left side of the wall. We can calculate as well the maximum passive pressure we have applying this formula, which is the area of this triangle basically, and using the coefficient of passive pressure. And we work out, we arrive to the conclusion that the passive pressure is considerable, and it's 2,334 kilonewtons. Is much more than we need. So in essence, we are in good conditions. But in this problem, because we have an additional P in here, we have to work out using the summation of forces in the horizontal direction. The P in equilibrium as well is another force that is necessary to be calculated and to be determined. So P will be equal to the summation of PA1 plus PA2 minus the passive pressure in equilibrium we just have calculated before, and the force P, the proper force, will be equal to 117 kilonewtons in this case. So we have more than 2,000 kilonewtons of passive pressure, a maximum passive pressure. It's greater than 481 kilonewtons, the passive pressure in equilibrium. So our safety factor in this case, which with the same geometry as the previous exercise for an unpropped wall, is 4.85. You see that adding this force P to this problem with the same dimension and the same properties for the soil and applying the same coefficient from the Euro codes increase considerably the value of the safety factor, because in essence we have more restrictions on the wall, so we have this force that is contributing to the stabilization of these walls. So propped walls in general works better than unpropped walls, but sometimes it's not possible to materialize this force on top of the walls, and we have to work with unpropped walls anyway, and we don't have any possibility. So remember that if the safety factor is equal to 1, you are about to fail, so you have to reinforce the wall immediately, and if you have a safety factor less than 1, it's better to run and reinforce pretty well the wall to avoid any accident or any problem. So I hope you understood this topic of thin walls inserted in the ground for simple cases. In this case, it's just a soil and which is basically sand and without water table. Remember that in reality everything is much more complicated. You usually will have a soil with several layers, and you will have the presence of the water tables in different levels, because the level of the water table will change with the season, during the seasons, and actually during the day you can have changes, and you will have to run several calculations in order to be sure that you are in good conditions for every single day of the lifetime of your extractor. Thank you very much for watching, and see you in the next video.